Swayam Prabha. Digital India. Educated India.
All right. So last Tuesday, I had introduced to you two methods to find the intersection between two solids. The first one was the select line method or the generator method, and the second one was the cutting plane method. So here is a little revision. Okay, so the first one is the generator method. Okay. Important points or salient features. Step 1, that's something which is critical. You have to figure out the view where the intersection points are obvious. Okay, and the way to figure that thing out is to figure if the intersection points are going to be lying on one of the solids. Look at the front view, look at the top view, and look at the profile view, and you will figure that your intersection points will be lying on this circle in the profile view. So once you've figured that thing out, the next thing you would do is you would generate a bunch of lines that would represent the surface of the other solid. You would generate again a bunch of lines that would represent the surface of the other solid. Okay? And that's the reason why the name, the generator method or the select line method. Step 2, use generators to represent the other solid. Okay? For example, this line would be a line on the slant surface of the cone. Okay? So this line is 311. Okay? Line 311. In fact, these are two lines. The first one is towards you, and the second one is away from you, that's behind the cone, right? So first one is towards you, the second one is behind the cone. Okay, and the best way to visualize this in the front view is this. So this is the first line, line 11, and this is the second line, line number 3. So this line that is on the slant surface of the cone is in fact representing two lines in the front view. Okay. And in the top view, of course, if you project this guy over here, this would be line 11, and this one here would be line number 3. Okay. Step 3, and this is something which is important. You have to exercise care in labeling and following them. If you don't label these lines properly and these intersection points properly, it will be difficult for you to connect the dots later on. Okay. Now, Vasu was asking me this before, how did I connect these intersection points here and here? So if I look at the intersection points on the circle in the profile view, I go A, B, C, D, E. So I go in order, and I follow the same order in the front view as well as in the top view. So I go A, B, okay, and then C, and then D, and then E, and so on. Likewise here, A, B, C, D, and so on. Now if you notice, from this height and above, okay, this part will be visible in the top view. So this part is going to be visible in the top view. Okay, and from D onwards, from this height down below, these guys will be hidden, they will be invisible. And that's the reason why these lines are shown using hidden lines or dotted lines. Okay. So you'll have to be very, very careful in following the labels properly, because if you don't, then you'll mess up the connections between the dots, between the intersection points. All right, so once you have all these lines ready, you figure out the intersection. For example, this is one of the intersection points. I call it I. I project it onto the front view. Now these are in fact two intersection points. Again, one is towards you and the other one is behind the cone. Okay. So this intersection points gets mapped at these 2 points in the front view. Okay. And these intersection points lie on lines or generators number 3 and 11 respectively. 3 and 11. Now which of these 3 and 11 generators is towards you? Is it 3 or is it 11? Okay, if you stand here and if you look at this view, which one of these will be towards you? All right. So once you have these intersection points, map them onto the front view. So this one will be lying on generator 11 and this one will be lying on generator number 3. Importantly, do not miss any intersection point. Okay. All right. So this was the select line method or the generator method, and it works only when the intersection points are obvious in one of the views. Okay. The other method was the cutting plane method. Okay, and look at these views for example, and the method works better when the intersection points are not obvious, and I'll give you an example later today. Okay. Step number 2, you should know what the intersection between the cutting plane and solids yield. For example, if I cut through this assembly of the cone and the cylinder through these horizontal planes, the intersection between the cone and the horizontal plane will be a circle, of course, and the intersection between the cylinder, this cylinder, and the horizontal plane will be a rectangle. So eventually determining intersection would boil down to determining the intersection between the circles and the rectangles in the top view. Okay. So this step is critical. You should know what the intersection between the cutting plane and solid yields. Okay. Let's take an example. So let's take plane D slicing the assembly of cone and cylinder. Okay. So corresponding to this plane, okay, the intersection between this plane and the cone gives me a circle. Okay, and the intersection between this plane and the cylinder gives me a rectangle. Okay, so in the top view, how many intersection points would you see? You would see 4 intersection points. So you need to compute the intersection. Number 1, number 2, number 3, and number 4. These intersection points are going to be lying on which plane in the front view? Plane number D, plane number 4. Okay, project points of intersection to the respective planes. So you are going to be drawing a bunch of lines, a bunch of circles, a bunch of arcs, and somewhere in between you'll be thoroughly confused and you'll be like, all right, so be very, very careful, and that's where labeling happens to be very important. All right, so all you need to do is project these points down onto the respective plane, and in this case these are the 2 intersection points in the front view. Okay. So summary of what we had discussed on Tuesday. Notice here that you will have 2 other intersection points on the back side of the cone. Okay. Which ones are going to be in the front? This one and this one. Which ones are going to be at the back? These 2 guys. Okay. Once again, do not miss out on any intersection point. Otherwise your connectivity will not be proper. So the connection or this contour, or rather these contours, will not be proper. All right. Another example. And I'll give you a slightly different angle to solve this. So this is the example of determining the intersection between two prisms, two rectangular prisms. One is vertical, the other one is horizontal. Okay? Inspect the three views. Are the intersection points obvious? Are the intersection points obvious? Yes or no? Yes. From where do you think you would be getting the intersection points? Profile view. Wonderful. Wonderful. So you can use the generator method to solve this, but I'll give you another method. And this is something along the lines of the lines and planes, the concepts that you had learned in previous lectures, hopefully. First thing you would want to do is start labeling. Okay, so PQRS is this prism that's penetrating the vertical prism inside. So P is actually a line, and so is Q, and so is R, and so is S. Okay. Okay, so P is this line, Q is a line which is closer to you or away from you? Which is closer, na? R, and then S is another horizontal line which is away from you. Okay. So if you go on to your top view, line P appears here, Q appears here, R again at the center, and S onto the top. Okay. All right. Label the vertical prism in the front view. So A, B, C, D. Okay, so this is A, B, back side or the back edge C, and D. And likewise over here, A comes from here, B comes from here, the center, C comes from the top over here, and D again at the center. Step 1, you have to do labeling properly. Okay. Now, you can think about these two prisms as being composed of 4 different planes. ABCD is composed of 4 planes, and PQRS is also composed of 4 planes. All right. So the problem boils down to figuring out the intersection between any two planes. So it's like a plane-plane intersection. Now, notice again that in the profile view, PQ, QR, RS and PS, they happen to be in the edge view. Okay. So this plane and this plane here, they happen to be all in the edge view, in the profile view. Okay. So it's easier for us to figure out the intersection between planes and planes if we have a view where one of the planes is in the edge view. Nah? All right, so extend this plane PQ. Where do you expect the first point of intersection? So if you are trying to figure the intersection between two planes AB and PQ, so this is plane AB and this is plane PQ, where do you expect your first point of intersection to be? Here? Okay? It's quite obvious, nah? It's quite obvious. Now this point of intersection is lying on which of the edges? Which of the edges in or on the vertical prism? A and? Do not miss any intersection point. A and? Would it be A? B and D, nah? So one point is here, the second point is here. All right. Now this point, the intersection corresponding to this point will not be obvious. And that's the reason why I had extended this plane. Now it's easier for me to locate this intersection point. Okay. So this intersection point will be lying on edge A. Okay, point number 2. But the intersection is actually happening here. But before that, plane-plane intersection would give me what? A line. Intersection between two planes implies a straight line. So one line would be this one, joining 1 and 2. The second line will be this one, joining 1 and 2. All right? Now my actual intersection is happening here. Right? So if I extend this edge QS, okay, these are the 2 points where my actual intersection is happening. Okay? All right? This is like a pseudo intersection point. This is not the real intersection point. This is where the actual intersections are happening, these 2 points. Okay? Having said that, it's actually the edge Q which is going inside, which is kind of hampering this intersection from happening. Okay? So you need to extend edge Q from both sides, because edge Q is going to be visible in the front view. Second guy, intersection between which of the 2 planes? QR and, well, are you solving the intersection between 2 planes or 3 planes? Notice, this is QR, and QR is intersecting with plane AB and plane AD on the back side. So be very careful, and that's the reason why labels help. All right, so extend this. One obvious intersection point is point number 3. This point on the vertical prism is going to be lying on edges B and D. Okay, so this point 3 will lie here. This point 3 will lie here. Okay, and this pseudo intersection point, that will lie on A. If I call it point number 4, extend it, it will lie here. Again, intersection between 2 planes will give me a straight line. In this case, that straight line will be joining points 3 and 4. I'll get one of these and the second one of these. Okay. Once again, this is not my actual intersection point. Actual intersection is happening over here. All right. So my intersection lines, they get extended only to this point. Okay. RS, point number 5. Project that, point number 4 and 5, they will be essentially here at the same point. PQ, extend that, get the pseudo intersection point number 6, project that, your point number 6 will be here. Okay? Relatively simpler example. Now notice that the intersection between plane RS and the back side of the vertical prism is hidden, and so is the intersection line between PS and the back side of the prism, and they are hidden precisely behind these lines, and that's the reason why they are not visible. So that's something that you'll have to keep in mind. All right, so the horizontal prism is penetrating inside the vertical prism, so you'll have a hidden line there, a hidden line there. Okay, and a hidden line there. Notice how these 2 points, they correlate with the top view. So if you take the projections up from these 2 points, this is where they occur. Won't there be a hidden line? That's what my next question is. Think and analyze. What do you have to think about, or what do you have to say about these hidden lines? This one, and this one. Are they going to be there, or are they not going to be there? Are they going to be there, or are they not going to be there? I for the drawing. Nah? Think about that. All right, so let me do a little what we say in IIT Bombay, Kira. You know what Kira is? So it's one of the lingo words in IIT Bombay. So this was a relatively simpler example. So let me rotate this horizontal prism by some angle and see how interesting my problem becomes. Okay, I rotate it clockwise by some angle. Similar story. Intersection between two planes, 4 planes forming a vertical prism, 4 planes forming a horizontal prism. The labels happen to be the same. You know, PQ, QR, RS and PS, they all happen to appear in the edge view, in the profile view. Okay? So it's kind of obvious for me to extract the intersection point information from the profile view. Okay. Having said that, now of course, when I rotate this horizontal prism PQRS, the corresponding projections in the front view and the top view, they'll change. Now, okay. First intersection point. Okay, we need to figure out the intersection visibility of both the prisms. Extend this prism. So you'll have one intersection point, pseudo intersection point. Okay, now do you say that the first intersection point, which is kind of obvious, is going to be this one? Yes? Where is that intersection point going to lie? BD. All right. This is my second section point, pseudo intersection point, not real. Project this guy onto B and D. So this is 1 and this is 1. So notice that I am labeling my intersection points as I identify them and as I project them onto different views. Okay? Because if I don't, you know what's going to happen. Project point number 2. Point number 2 is going to be lying on edge A, not C, but A. Okay. Intersection of 2 planes, they give me a line. So the real intersection is going to be happening here, okay, at point number 3. Likewise, over there at point number 3. I'm not formalizing my drawings as yet. I'll go forward. I'll extend QR. Now in this case, I don't have real intersection points here and here. So I'll need to extend this plane on both sides till I hit the 2 edges of the vertical prism. Okay? Pseudo intersection point number 4 and number 5. 4 lies on edge A, project that. This is where my 4 is. 5 lies on B and D, project these. Okay, and this is where point number 5 or points number 5 they lie. Straight lines joining 4 and 5. Okay, so if you extend this plane, 4 and 5 will be the actual straight line between the 2 planes that will be representing the intersection between 2 of them. Okay, this is point number 6, which is the actual or real intersection. And point number 6 is going to be lying on 4, 5 here and here. Okay. Point number 6 is there and 6 is there. With me? With me? Let's continue. Extend this guy. Once again, we'll get 2 pseudo intersection points. Number 7, number 8. 7 lies on A. 8 lies on edge C of the vertical prism. Project 7. 7 lies on A. 8 lies on C, the back side. The back side. Alright, so 7 and 8 will be a straight line, alright. Point number 9, this is where the actual intersection is happening. project that, number 9 would lie on B and D. B and D. So 9 would lie here on B and it would lie here on D. Okay, and the actual intersection line will be the line joining points 8 and 9, there and there. Okay, but this one is the actual intersection point. Okay, so if I project that, identified as 10, if I project that, point number 10 is here and here. Messy, already messy. Okay, and the final thing, extend PS, identify that intersection point as 11, this one as 12, project 11, 11 is going to be lying on the back side of the vertical prism C, and 12 will be lying on B and D. Okay, join 11 and 12, or maybe join 10 and 12. In fact, they would essentially happen to be on the same straight line. Okay, same straight line. So join 11 and 12. Okay, the actual intersection is happening here. Okay. All right. 13. 13 lies somewhere over here and here. Once you have identified these intersection points, now you need to connect them. Which ones of these will be real? Which ones of these will not be real? All those points which lie on the horizontal prism, for example 1, 3, 6, 9, 10 and 13, they will be real intersection points. Okay? Number 1, number 3, number 6, number 9, 10 and 13. Once you identify the loop, the connectivity, you can connect the dots in the front view. Okay? Now 1 to 3, is that line going to be visible? 1 to 3. Line 1, 3, is that going to be visible? Well, of course, you need to project these intersection points up. Okay, that is something which is going to be a little tedious, but you should be able to do that. Okay, this would be an exercise for you. All right, so line 1, 3, that's going to be visible. How about the next one, 3, 6? 3, 6, is that going to be visible? Now 6 to 9. It will be a hidden line because it's going to be on the back side of this prism. Okay, if you are looking at the assembly from here, this guy is going to be behind. Okay, 9 to 10. 9 to 10, visible, not visible. 10 to 13, visible, not visible. Hidden. 13 to 1. 13 to 1. You need to be a little careful because this guy here. Although it might appear to you that this would be visible, actually these 2 points are lying on the back side of the vertical prism. So be very, very careful. Be very careful. This would be hidden. Okay. So the previous example was quite straightforward. This line and this line they merged. This line and this line they merged, and you actually got a very nice V-shaped thing. This one is quite tedious. So very nice example of how labeling helps you connect the dots better. Yeah.
Yeah.
Sir, will not have to make any oblique lines. Work will be
it with only vertical and horizontal projections?
You can, if you want to.
So it will be not
Easier, less messy. Yeah, you can. You can. All right. You figure out the visibility of the prisms now. Okay, figure out the visibility of the prisms. So you know the concepts from lines and planes, the visibility. Try to figure that thing out. I won't say a word. I'll just keep flashing different lines, which are going to be green in color. Okay. This is going to be visible. That will be visible. This will be visible. This one here will be hidden. Huh? Why is that? Why is that? S is on the back side. Yeah. This guy here, this line here is hidden. Okay. And so is this line. Okay. Mirror image the same thing and you will get the result. This line is going to be hidden. Okay, P is inside or P is penetrating the vertical prism and so is R. What about 3, 3, 10, 10? This guy and this guy? Yeah? Yeah.
So we say that one solid has been cut through and other has been solid.
Yeah.
So suppose both are equal in size and it is place symmetry, then we cannot tell which is removed and which is into it. So in that case, you will make dotted this one.
If they are equal in size.
Or in the model that we had drawn yesterday,
Yeah.
in that model we couldn't tell whether the code was cut or not.
Okay. No, it was no. In that model, it was the cone that was cut. It's quite obvious.
Okay, say if the faces were opaque, then we would have made it different. The cylinder was hollow, that's why we could tell that it was the cone that was.
Yeah.
Another thing, these are both solid, so won't the glass or anything get just touch and we will not be able to see the, because they are solid, we cannot distinguish between them.
What? Come again?
Both of these are solid and they are exactly fitting into each other.
Yeah.
So we cannot distinguish between them unless.
Which one has been cut and which one has not been cut? If they are of the same size. No, no.
So both of them are solid here. So suppose they are made up of clay, in that case you cannot distinguish which is which one. They are just acting as a single piece,
Yeah.
not as two different parts.
Hmm. So
There should be no lines actually between denoting any one of them.
there should be.
No lines inside the.
So you're saying that there should not be any lines here because you don't have much clue about which one is penetrating which one.
And he said that
Is
penetrate to it should be a single solid.
This can be a single piece only.
this could be a single piece. Yeah. This could be a single piece. Yeah.
In that case, we will not make lines inside.
True. True.
How can we distinguish that this is not a single piece? It should be taken as a single piece of solid.
So the question is this. So given two prisms, the horizontal one, the vertical one, how do you figure which one is penetrating the other one? Okay, number one. Question number two, or related question is, what if the entire thing is a single piece, that none of the prism is penetrating the other one? So if the latter is the case, then these horizontal lines may not be shown, but if the former is the case, then you need to show those horizontal lines. And the Q has to be derived from the three views that are given to you. The clue has to be taken from the three views which are given to you.
If we have to draw these lines, the 30, 33, 15, and 66.
Yeah.
Why isn't it shown in the question in the top view or the side?
I haven't actually shown the intersection in the top view, or have I? Yeah, yeah. So no. So you guys are in a habit of getting everything on the plate, nah? Don't.
So if the question says that it's a single piece, then we have to.
You figure it out. There has to be some thinking and analyzing that you need to do. So if you are going to be using, or if you are going to be drawing these lines, of course you need to figure out the corresponding lines, whether they're going to be there or not in the top view. You figure it out.
I'm saying that how does the question communicate to us whether the whole thing is a single solid or there is a manipulation?
I have to go. How does the three views communicate to you if one of the solids is penetrating the other solid? What if I give that information that one of the solids is penetrating the other solid? Then it's going to be clear? Otherwise, it's not going to be clear. So assume that I'm going to be giving that information to you. All right, so this one is quite interesting. Intersection between two cones, a vertical cone and a horizontal cone. The three views are shown to you. And my first question is, are the intersection points obvious from these three views? Are the intersection points obvious from these three views? Is it possible for you to figure out the intersection points just by inspecting each of these views? Yeah or no? 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 So it's not going to be easy for you to use the generator method or the select line method. So instead you would want to use the cutting plane method. So the intersection points, to me at least, they don't seem to be obvious. Use the cutting plane method. Okay? So use a bunch of horizontal planes slicing the assembly of these two cones. Okay? Now if you slice the assembly using a bunch of these horizontal planes, intersection between one horizontal plane and this vertical cone will give you what? It will give you a circle. Intersection between the same horizontal plane and this horizontal cone is going to be giving you what? A hyperbola. So your intersection problem, your problem of intersection boils down to figuring out the intersection between the circle and a hyperbola. Okay? All right. Now, what I've done is I have, used the information that the intersection is going to be over here, intersection is going to be happening over here, here, and here, and correspondingly, I have chosen the respective horizontal planes to slice the assembly. It makes my work a little easier, but I do not guarantee that my solution is going to be accurate. Okay? For more accurate solution, you should be using more number of horizontal planes slicing the assembly of these cones. Okay? So the first horizontal plane is this one, second one is this one, third one is the center, or third one contains the axis of the horizontal cone, fourth one, and the fifth one. Okay? Now follow this very carefully because things are going to be a little messy. Alright, so plane number one. If I look at the intersection between horizontal plane number one and the vertical cone, I am going to be expecting a circle in the top view. Okay? And this plane, when cutting this cone, will give me a hyperbola. The vertex of the hyperbola is going to be lying over here. So essentially, I'll be expecting a single point of intersection. There. And there. Okay? Okay? Stay with me, stay with me, stay with me, stay with me. Stay with me. Now this one is just a fluke. I don't need to actually draw this because I know the intersection point is just going to be a single intersection point. Wait for the rest of the construction. Alright, so plane number 2 intersecting with the vertical cone will give me this circle, and when intersecting with the horizontal cone will give me a hyperbola. The vertex of that hyperbola is going to be here. Okay, we need to construct it. We need to construct that hyperbola. So for that, how's the base of the hyperbola going to be? How's the base of the hyperbola going to be? So the 2 points which will be lying on this edge of the horizontal cone, they are going to be separated by twice this distance, from here to here and from here to here, 1 and 2. Once I know that, and once I know the fact that my apex or the vertex of the hyperbola is going to be lying over here, I can draw a box. Once I draw a box, I would divide this edge of the box into equal number of parts and this edge of the box into equal number of parts. Okay? Now from this point, I'm going to be joining all the points on this edge, and from this point, the apex of the cone, I'm going to be joining all these guys. Alright? Okay, so let's say equal number of parts. I'm just using a bunch of points for demonstration, not so very many. Join this point of the box with that point over there on that edge. Okay, likewise for the second set, this one with this one and this one with this one. Okay, so you'll get a bunch of intersection points. So intersection between this line and this line, which is this point here, will give you the first point on the hyperbola, and intersection between this line and this one here will give you the second point. Okay, 2 points. You already know that this point is going to be lying on the hyperbola, the vertex. Draw this hyperbola. Draw the mirror image of that. Okay, so once you have the hyperbola in order, find the intersection between the circle and the hyperbola. Okay, this guy projected down onto the same plane. This guy projected down onto the same plane. So this would be one intersection point, 2 intersection points over here, and this one. Okay. Plane number 3 and the assembly. The vertical cone will give me a circle. The horizontal cone will give me kind of a triangle. So intersection points, getting that is not a problem. 2 intersection points over here and 2 intersection points over there being projected downward onto plane number 3. You'll get these 2 points. Plane number 4, again, the vertical cone is going to be giving me a circle. The horizontal cone is going to be giving me a hyperbola. So you need to draw that hyperbola. I'll quickly go through that. So measure this distance, make that distance over there and over there. Okay, draw this box, the same construction procedure. Okay, divide this edge into equal number of parts, that edge into equal number of parts. Okay, start joining the lines, find the intersection points. You'll have 4 intersection points in all, or 4 points lying on a hyperbola in all. Draw that hyperbola, draw the mirror image of that, find the intersection between the corresponding circle and the hyperbola. Okay, so of course one point will be here and the other point will be here. And of course, there would be a corresponding point at the top. Okay? And the fifth point is quite obvious. I mean, it has to be lying here. So you don't need to worry about that construction at all. It's quite messy. So I can really understand the expression on your face. Yeah. Okay, so once you figure out the intersection points, as I said, the number of planes that I have chosen, they are not adequate. Okay, so they have to be adequate for you to get the actual contour of intersection. That's the first one, that's the second one. Okay, and if you realize, if you map these intersection points properly in the top view, these are going to be shown in red. Join them. Get the mirror image of these. This is how your cone assembly is going to be looking in the front view and in the top view. Now here I am assuming that the horizontal cone is absent. So what it has done is it has cut away a portion from the vertical cone and like just gone for a ride. Okay, and that's one of the reasons why this part is visible. Otherwise, this part would have been, below the cone. So that is something that you need to be a little careful about. Okay, and once again, if you want to compare this drawing with AutoCAD, work it out, cone interaction, place your cones properly. This is how it's going to look. Now, Avikalp. So I was interacting with him yesterday, right? And he was like, you showed that cone hexagonal prism assembly yesterday or Tuesday, and how did you cut the cone? For your hexagonal prism to be fit precisely into it. And to which I said, well, if you want to learn how to cut it, first you have to figure out the intersection contour between the two solids and use the information that one of the solids is developable. In fact, in the example on Tuesday, both the solids are developable. Okay, use the fact that the cone is developable, cut the cone, spread it out. You already have the intersection contour in there. Cut that part out. Flap or fold your cone back into shape, and then you have the slot. So the first part, intersection, is something that is covered, that has been covered today and last Tuesday. Development will involve 2 more lectures next week, and then you will learn how to cut one solid to be able to precisely fit the other one.